In this lecture, we will complete our discussion on flow through converging diverging nozzle, and we will further discuss about flow past and airfoil over a range of free stream Mach numbers. We will do a quick recapitulation of some important relations for isentropic flow through CD nozzles. We learnt about the area velocity relation, and we learned that for subsonic conditions, if area decreases, velocity increases and vice versa. For supersonic conditions, if area increases, velocity increases and vice versa, which is slightly counterintuitive, but we know that from the area velocity relation, that is how it works. And therefore, we have an accelerating isentropic flow through a supersonic nozzle, while a decelerating isentropic flow through a supersonic diffuser. We further learned about the area Mach number relation, where we express the area ratio as a function of local Mach number, and we also discussed that if we are given a converging diverging passage, then for a given area ratio, there are two locations which we will see in this CD nozzle, where the Mach number on one hand would be subsonic, while on the other it will be supersonic. And we additionally mention that the m star is a function of m. By definition, it is u by a star, which is u by under root gamma r t star, and further you can try to prove for yourself that this is how we can express it in terms of the local Mach number. So, that is a small homework problem for you. So, Mach number at any location in the duct is a function of the ratio of local duct area to the sonic throat area. So, that is the A by A star that we are talking about, or the area ratio. And under isentropic flow conditions, we have to remember that A by A star is always greater than equal to 1. The lowest that A can go is to the A star condition, which is at the throat, when it can go sonic. Some more important relations related to the sonic condition at the throat. We know that if you reach sonic condition at the throat, the flow further gets choked. That means, that is the maximum mass flow rate that particular throat can allow through the nozzle, and you cannot enhance the mass flow rate beyond that point. It is given by rho star u star into A star. A star happens to be the throat area itself. So, for a sonic condition at the throat, A or A t is equal to A star, u star is equal to A star, m star is equal to 1. Of course, m is also equal to 1. So, at sonic condition, m and m star are identical. Now, in this equation, if you really want to work out the rho star u star, then how do you do it in terms of the stagnation properties? This is how you do it. So, these are the relations for rho star u star, which you can plug in and work it out in the m dot equation. So, u star is given by this relation where t star is involved, and then again p star is expressed in terms of t naught. Another set of important relations, that from isentropic relations for p by p naught and t by t naught, you get these ratios for a choke flow in the throat. So, these would be very useful relations to remember. And in our last lecture, we had been discussing about flow through the CD nozzle. As we change the back pressure, how does it change? So, we had started the discussion and we reached up to a point where the Mach number was just reaching sonic condition at the throat. What happens if you reduce the back pressure further. So, that is what we are going to discuss in the next few minutes. We also recall that the moment the Mach number reaches 1 at the throat, the flow gets choked. The variation upstream of the throat now gets frozen. That means, there will be no changes further in the way the Mach number changed upstream of the throat. So, these are very important things to remember. Okay. Now, let us try to make a few plots to explain what happens if you change the back pressure further. Remember that we are using the terminology back pressure or exit pressure, P exit or P back, they essentially mean the same. In this plot, we are going to show the Mach number variation as a function of x, let us say, and this is the location where Mach 1 condition has been reached. That means, it is the throat, you have a choked flow here. So, if you were to draw the nozzle, this would be the minimum cross sectional area and then it expands. So, we are just drawing half of the nozzle because it is symmetric, and if you have an isentropic flow beyond the throat where the flow can accelerate further, this is the supersonic branch of the flow. This is the subsonic branch, and remember that this branch is now frozen. This is what we have to keep in mind. We recall having drawn other plots where the Mach number would decrease and then you would have a subsonic flow downstream, and we had talked about PE3 condition, which would have created a ME3 Mach number at the exit. So, that is a subsonic isentropic flow, while this is a supersonic isentropic flow. All right. Now, if you have this back pressure, then you will have a supersonic isentropic flow. What if the back pressure is increased slightly? Then you will not be able to achieve isentropic supersonic flow all through the nozzle. Somewhere in between, the flow will terminate in a shock. A normal shock may be formed in the diverging part of the nozzle, here in the nozzle, and the moment it happens, you have a subsonic flow and you are giving it an increasing area, and therefore, it will slow down further, and that is how the Mach number keeps decreasing till it reaches the exit if you are increasing the area. So, going by the geometric feature, that is how it is going to happen. What if you are having a slightly different pressure in the exit end, but it is still not as strong that it can create a normal shock within the nozzle. So, there are other possibilities which can occur. So, let us try to figure out what those possibilities are. So, let us additionally make a pressure plot. So, we tried to understand through the Mach number plot how things are working. Now, let us try to work out how in terms of pressure the things are happening. So, the first case will be the isentropic expansion to supersonic condition. So, we will draw that plot first. That is how it will expand to the exit pressure. Let us give it some name. We will give it a name, say PEI. Okay. We will also give this a name, say MEI. So, the E stands for exit, exit plane, all right, and I for isentropic. So, what is the corresponding pressure in the exit plane? It is PEI. What is the pressure corresponding to the normal shock formation here? Let us try to make the plot for that. So, when the normal shock forms, the pressure distribution looks more like this. Let us call it P E 4. Let us superimpose the P E 3 over this plot. P E 3 was somewhere here, where you had an isentropic subsonic part. Here, on the other hand, you have a supersonic branch followed by the shock and a subsonic branch. That means, the flow does not remain isentropic anymore. So, there is an upstream entropy, there is a downstream entropy, and there is a rise in entropy in this case. While in the previous one, the downstream entropy was exactly equal to the upstream entropy. So, that is the difference we have to keep in mind. Are there any other possibilities? Well, the answer is yes. Interestingly, the answer is yes. What are the other possibilities? For that, let us try to sketch the flow field to understand the other possibilities. One possibility is that the normal shock occurs at the exit plane. So, the flow all through the nozzle remains isentropic, but suddenly at the exit you have a normal shock. This is one possibility. What are the other possibilities? Well, you could have an oblique shock, a pair of oblique shocks at the exit plane. That is another possibility. You could have still another possibility, that is, you can have expansion fan outside the exit plane. Which was the possibility for MEI or PEI case? That case gave you a supersonic jet which was just moving out straight without creating any further waves in the flow field. So, this is the case for MEI or PEI. What about the rest? The rest are interesting cases. So, this is normal shock at the exit plane, this is oblique shock at the exit plane, this is expansion fan at the exit plane. Where will the pressures really figure? Let us mark these pressures. We will define a few pressures here. Let this exit pressure be P E 4, another pressure be P E 5, sorry, P E 4 we have already marked, let this be 5, another be P E 6, and still another one we will mark below the PEI, which we will call as P E 7. So, which are the cases? This is the P E 5 case, where the exit pressure is slightly lower than the P E 4 case. So, that the normal shock does not form inside the diverging part of the CD nozzle, but rather moves to the exit plane. So, that is P E 5. What is P E 6? We say it is an over expanded case, over expanded flow. That means, you have expanded it slightly higher than the condition for PEI, and therefore, the pressure has dropped a little lower than the back pressure, and it is adjusting through the formation of an oblique shock. It does not need as strong a shock as the normal shock, it can adjust through an oblique shock, and that is what gives you an over expanded flow. And there is still another case which is called as the under expanded flow. That means, by the time it reaches the exit plane, you have to expand it further. It is still not expanded enough, and how does it expand? It expands through the formation of a Prandtl-Meyer expansion fan. So, these are the different possibilities that we are seeing for a converging diverging nozzle of a purely isentropic flow, or shock inside, or shocks outside, or expansion fan outside. So, with this we end the discussion on flow through converging diverging nozzle. Let us move on further So, we will now discuss about flow past an airfoil or a wedge over a range of free stream Mach numbers. So, it is better to add the word free stream Mach number, and we are coming towards the end of our discussion on compressible flows. So, we now have a fair idea about range of Mach numbers which can occur in a compressible flow. So, they can vary from subsonic compressible flow to a transonic flow, which is around the Mach number 1 range. We will discuss more about it. Then Mach number greater than 1 and much greater than 1, which we call as hypersonic flow. So, when you have a flow past an airfoil, typically with a free stream Mach number of about 0.7, the flow is subsonic in the free stream, but it is accelerating on the airfoil surface and maybe getting close enough to the Mach 1 condition. We have a particular value of the free stream Mach number where it reaches exactly Mach 1 somewhere on the surface of the airfoil, and that is a very special point, of course, on the surface of the airfoil. Where that happens to the minimum pressure point on the airfoil. So, on cambered airfoils you will usually find it on the upper surface. There is one point which is the minimum pressure point where this actually occurs. All right. So, if you increase the free stream Mach number further, that means you are going beyond the critical Mach number. Let us mark the critical Mach number as say MCR. So, your Mach number is now increasing beyond the critical Mach number. What will happen is that the Mach 1 condition will not remain confined to a single point. There will be a pocket which will develop over the upper surface first and followed by the lower surface as well. There would be pockets of supersonic flow formed on the airfoil, and then you are gradually getting into the transonic flow range. So, before the critical Mach number you have a subsonic flow all over. So, that was this regime, and then you went into the critical Mach number and you have just a single point on the airfoil where Mach number has reached 1. If you push the free stream Mach number further, you get into the transonic flow where pockets of supersonic flow now form, and if they form, they are usually terminated by a shock at the end of the supersonic flow packet or pocket, whatever you call it, and then there could be accompanying issues of drag increase which will happen with the formation of those pockets of supersonic flow and the terminating shocks. Now, as you move beyond the critical Mach number, there is a point which we call as the drag divergence Mach number, beyond which the drag starts increasing quite dramatically, and sometimes the drag increase could be manifold, maybe one order higher. That means about 10 times higher than what you had before the critical Mach number. So, this drag is usually a drag which is associated with both the wave drag aspect as well as additional flow separation, which are caused due to the formation of the normal shock waves at the end of those pockets of supersonic flow. And then you further accelerate the flow to say a Mach 1 condition in the free stream, and then these pockets get larger and you can have much higher Mach numbers within these pockets going beyond sonic condition to an order of 1.2, 1.3 or maybe even higher. It depends on the shape of the airfoil, its angle of attack and so on. And these Mach numbers could be quite high if the airfoil is reasonably thick. So, thick airfoils are not really supposed to operate at those Mach numbers, but if they are used, then they become aerodynamically inefficient because of very large drag increases. And this is where comes the utility of supercritical airfoils, which can suppress these flow separations and associated complexities with shock formation, and therefore, the drag can be dramatically reduced. If you have strong shock formation, there is also additional complication of what is called as shock wave boundary layer interaction. So, let us make a simple sketch to explain further about how the drag increase really happens. So, let us say we plot the drag along the y axis and the Mach number along the x axis. So, the drag is more or less constant up to the critical Mach number and slightly beyond, and then it starts growing. and growing quite rapidly, very sharply, and then it reaches a kind of a pinnacle before it starts dropping, and that's going to happen at a free stream Mach number of about 1. So, theory says that there is a very large increase in the drag in that range, but in reality we have a finite drag, but that is significantly more than the drag at these Mach numbers. And drag divergence Mach number is typically in this range from where the drag increase is happening very rapidly. And as we said that in thicker airfoils, which are apparently meant for operation at much lower Mach numbers, you have strong shocks formed on the upper and lower surfaces, and usually these shocks would interact with the viscous flow, the boundary layer, and make them separate. Therefore, you have large separations produced where the shock interferes with the boundary layer, and you have a large wake region found behind the shock. That means the drag will rise significantly. If on the other hand you have a more specialized airfoil meant for these Mach numbers, typically flatter supercritical airfoils, then we find that shocks still form, but they are weaker than the thicker airfoils. And consequently, their aerodynamic performance is much better in these Mach number ranges. You will also have a much thinner separated flow in the wake. So, compared to the drag rise in the thicker airfoil case, this will be lesser. There would certainly be drag rise with increase in Mach number, but it will be still within an acceptable range. Now, if it was a theoretically considered inviscid flow, then there would be no problems with flow separation. But in reality, when the shocks impinge on the viscous region near to the wall, that is the boundary layer, there is something called as the shock wave boundary layer interaction, which we have mentioned about over here. That is a complex phenomena, but that is a reality, and that has to be faced and managed well. So, let us very briefly discuss about that. Shock wave boundary layer interaction do occur on transonic aircraft wings, which we are discussing about. They occur in other vehicles as well. They occur even in hypersonic vehicles, engine intakes, and so on. And if you zoom deep into the region where the shock has impinged on the boundary layer, this is something what you will see. Here incidentally, the shock is coming in at an angle which is closer to an oblique shock, but the kind of shock we were discussing with reference to the airfoil is closer to a normal shock. So, there the shock would be looking more like this. So, that is a stronger one which is impinging on the boundary layer, and what happens is that the shock produces an adverse pressure gradient which makes the boundary layer separate, and there is a separation bubble formed below. The flow streamlines lift off from the surface, and they manage to go back and reattach after some distance. That produces a kind of a separation bubble situation when a shock interferes with a boundary layer. So, the adverse pressure gradient causes the boundary layer to separate, and it produces a flow separation bubble. Now, the moment the flow separation is created, it has a ramp like action or compression action on the incoming supersonic flow, and therefore, there is a formation of an additional shock because of the turning of the flow. So, this is purely due to the ramp effect produced by the separation bubble. Now, the interaction of the incident shock and the separation shock generates additional shocks, which we call as transmitted shocks. So, one arm of that transmitted shock goes and interferes with the viscous layer and the sonic line gives you the Mach 1 value. Below the sonic line, the flow further decelerates, it is subsonic. Above it, it is supersonic. So, the shock cannot exist in the subsonic range, it can go only up to the sonic line, and then it reflects back as a Prandtl-Meyer expansion wave, because there is a nearly constant pressure level in the bubble. And there are certain rules of reflection of waves which we will see soon at the bottom. And this basically follows the rule in the sense that a shock is reaching a constant pressure region and then it is reflecting back not as a shock, but rather as an expansion wave. So, please take note of that. And then once that expansion wave has formed over here, it deflects the shear layer towards the wall, where it is going to eventually reattach. So, this is where it goes back and reattaches. When it reattaches, there is a compression effect, out of which there is a reattachment shock which is produced, and this is what you see over here. Now, we were talking about rules for wave reflection, and we have included two cases. One is when a wave reflects from a solid boundary, another is when it reflects from a constant pressure fluid boundary. So, what are the rules? When waves incident on a solid boundary reflect in like manner, that is, a compression wave reflects as a compression and an expansion wave reflects as an expansion. So, solid boundary does not change the nature on reflection, but what happens when a wave is incident on a constant pressure fluid boundary? It produces a wave of opposite nature. So, a compression wave reflects as an expansion, that is what is happening over here. A compression wave coming in here reflecting back as an expansion wave. While if there is an expansion wave impinging on a constant pressure boundary, it will reflect as a compression. So, please take note of these rules. We are not trying to prove them here, but we are accepting them as facts. Let us move on further. If m infinity is increased to slightly above unity, this shock pattern will move to the trailing edge of the airfoil, and a second shock wave appears upstream of the leading edge. So, let us make a sketch to explain. So, this is your airfoil. Let us say your freestream Mach number is in this range. There is a detached bow shock, a subsonic pocket produced here. There is a supersonic flow moving past the airfoil, and what happens at the trailing edge? You have a very interesting flow structure which looks more like this. So, this is typical nature of transonic flow at a slightly higher end of the Mach number range. So, you have a bow shock ahead, and then you have a shock structure at the trailing edge. Mind it that these shocks earlier were on the airfoil surface, which has now moved further downstream, and they are there at the trailing edge region. If you were to insert a sharper body into this supersonic flow, then what would you see? A sharp nose body, then you will see a feature like this, an attached straight oblique shock, and this would end up producing lesser wave drag. So, these kind of sharper shapes are more preferred at supersonic speeds with a lesser drag penalty, and you now know how to draw the flow field. So, there will be an expansion here further because the flow is turning away. So, how would the streamlines come in? They will come in like this, they will turn slightly through the expansion and become like this. I am not drawing it at the lower part, you can do it yourself later on. And then if you push the free stream Mach number further quite significantly, it becomes much higher. In many references say a ballpark Mach number of about 5, but more importantly there are certain significant changes which happen in the flow field. That is how we need to demarcate the much higher supersonic range, which we call as the hypersonic range. So, what happens? we have the shock moving very close to the body, and the region behind the shock and the region just above the body, that becomes a very hot region. So, we say it is a thin shock layer, and it is so hot that the gas can get ionized. There are more issues with the hypersonic flow, which we will discuss later, but for the sake of completeness, let us make a very small sketch here, so that you have a good idea of the entire range of Mach numbers. As we were saying, that the shock is very close to the body, and the flow which is lying in between the shock and the body we call as a shock layer, that is a very thin one and it is very hot. So, let us try to sum up. In this lecture, we completed our discussion on flow through a converging diverging nozzle under different back pressure, and we discussed about isentropic as well as non-isentropic cases. We studied both shocked flows and isentropic flows. Subsequently, we discussed about flow past an airfoil as well as wedge over a range of free stream Mach numbers, spanning from moderately compressible subsonic flow to highly compressible hypersonic flows. Thank you.